Alright, what's up, guys? Back with the second problem from the MIT Integration B 2018 qualifying exam. And this one is kind of a beast. Um, so we got the integral of the square root of x times, and we have this quantity on here, which is the cube root of x times. And we have, it's kind of a nested sort of deal with the fourth root of x and the fifth root of x and so on. So we have the sixth and seventh and eighth. And that would go, the dot 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 assumes it goes on forever. So you can't really do any other thing other than try and find some sort of trick and make it look like something that we can work with. That being said, it is kind of hard to get a feel for where we should start. But what I'm going to do is I'm going to say, okay, I can maybe split up this square root into kind of having this first deal and maybe that second deal. And we'll start there. So we can split the integral into saying it's the integral of the square root of x times the square root of kind of all the rest of that. So that's the cube root of x, the fourth root of x, and the fifth root of x, and kind of and all that jazz. So we have kind of our square root times the kind of the rest of that dx, right? And so we can kind of do this for all the terms. Maybe we can do it for this x cubed term as well. We can say it's the integral of root x times the square root, and then we have cube root, so it's x to the 1/2 times x to the 1/2 times 1/3. So we can also write it as the sixth root, but I'm going to keep it as x to the 1/2 times 1/3. You'll see why in a second. Times 1/3 times kind of the rest of it, which is this part, which is the cube root of the fourth root of x and the fifth root of x, and that is encompassed by all of that. And there we go. Okay, so that kind of makes sense. We write that equation or that term as x to the 1/2. And if we keep doing this, we will end up with x to the 1/2 times x to the 1/2 times 3 times x to the 1/2 times 3 times 4, right? And that just keeps going, and so on. What we can do is we can say, okay, well, these all have the same base in different exponents, so we can combine the exponents with one common base. And so what we're going to do here is we're going to say, okay, we can combine the exponents like something like this. So it'll look like x to the 1/2 plus 1/2 times 3, right? Plus, and then kind of the rest of it, and then I'll keep going. But so we're writing it with one common base, and we're just adding all the exponents. So that's the exponent. We're just adding all of those, and so on. All right, I'm running out of space here, so I'm going to take this layer and move it down here. And we're going to start at the top, I guess. All right, so now we have our integral of x to the 1/2 plus 1/2 times 3 plus 2 times 3 times 4, and so on, and that's dx. And so maybe this is starting to look like something, if we recall from maybe pre-calculus or, I don't know where they teach this now, but it's definitely going to be used in calculus. It's definitely going to be probably taught in calculus 2 when you get to series. We know that the 1 times 2 times 3 times 4 all the way up to the nth, that's n factorial, the definition of n factorial. And all these terms here in the denominator, those are kind of that last term. So 4 here, 3 there, kind of 2 there. Those are that factorial, right? So 4 times 3 times 2 times 1. So that term is kind of 4 factorial. This term is kind of 3 factorial, or 1/3 factorial. That's 1/2 factorial there. So we can rewrite this whole integral as x times 1 over 2 exclamation point, 1 over 2 factorial times 1 over 3 factorial plus 1 over 4 factorial, right, and keep going. And now it might start looking like something. We know that e to the x, the series expansion of e to the x, you'll know this if you take second year calculus, maybe even third year calculus, depending on where you're taking it from. You'll start talking about series and sequences and how we can approximate series with functions. And so one of the first things you'll learn when you're doing that is that e to the x can be approximated by 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and that will go on forever. And I'll make a better approximation as you get on. But we start with not 1 or 1 over 1 factorial, we start with 1 over 2 factorial. And that's going to be this bit here. And so this term is 1, and 1 over, so 1 factorial here, 1 over 1 factorial, that's just 1. So collectively, these make 2. So if we say e to the x minus 2, that is going to be our exponent. So it's 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. So, running out of room here, remembering we have minus 2, we can rewrite the entire integral as the integral of x to the e to the x minus 2 dx. And now that is completely doable. Remembering that e to the x here, that whole exponent is just going to be some number. So e to the x is not it's not x to the e. It's not like x squared, x cubed, but it actually is just a constant. And so e to the x minus 2 is going to be just a constant. So we can treat it using the same basic integral rules we learned in Calculus 1. So we can take the power, subtract 1, and then divide by that new power. It's kind of the rule we learned in first year calculus. And we will have our answer, which is x to the e to the x and power of the original function minus 1, so, plus 1, so it makes e to the x minus 1, that's what I was saying, divided by the new power minus 1 plus c, constant of integration, and that is the answer. It's kind of a beast. Alright, thanks for sticking with me. We'll see you on the next one.